decimal expansion of rational numbers. Now, what is a rational number? A rational number is any number which is any fraction, to be specific, which can be represented in the form of p by q, where p and q both must be integers. That means whole numbers which can be negative or positive. -2, +3, 4, 0, 1, 2. Any of these numbers are integers. Now p and q must be integers, but q, the denominator, must not be equals to 0. This is a condition, because if q is 0, the whole fraction will go to infinity. It will tend to infinity. Anything divided by 0 will give you infinity. So any number which can be represented in this way is a rational number. Now we'll talk about the decimal expansion of these numbers. When we convert these numbers into decimal numbers, we get two types of numbers, two types of decimal numbers. One is terminating, which means ending, the digits end, and the other is non-terminating, but repeating. The digits are repeating of this kind of decimal number. They go on forever, but the digits which go on have a specific pattern. They repeat in fixed patterns. So let us take examples of both. For example, 1 by 4. The decimal expansion is 0.25. This is a terminating decimal number because it ends at 5. For a non-terminating repeating, you can take 1 by 3. You get 0.333333. So this goes on forever, and the digit which repeats is 3. Now there can be other numbers where more than one digit will repeat. For example, if you take the example of 2 by 11, let's say, here you will get 0.18181818. So here the pattern which is repeating is 18. These two digits repeat 181818. All right. So the two characteristics of this kind of number is that the digits will go on forever. They will never end, non-terminating, and they will repeat in a fixed pattern. Now we'll talk more about both the numbers and their properties. In case of a terminating number which ends, whose digits end, they don't go on forever, for this kind of number, we have a property that the fractional form of this number, that is p over q, in this number, q, the denominator, can be written in the form of 2 and 5, in the multiples of 2 and 5. That means the denominator must have its prime factors as 2 and 5 only. 2 to the power n and 5 to the power m. That means the denominator must be comprised of 2 and 5 multiples only. If you have this kind of a rational number, then the decimal expansion of this rational number must be terminating. It must end. Okay. Now here 2 raised to the n and 5 raised to the m, which means that 2 can be multiplied any number of times and 5 can be multiplied any number of times, and n and m both should be positive, obviously, because if it is negative, you will get a decimal number. But here we are only talking about the prime factors. So n and m both should be positive integers. Let's take an example of this kind of number and see how this property applies to it. Let's say we are taking minus 15.15. Now we want to see whether, now this is a terminating number, so it must follow this property. So let's first convert this into a fractional form. For converting it into fractional form, we'll multiply the denominator and the numerator by 100. So we will get minus 1515. The point will go away after multiplying both the sides. You will get 100 here. Now when you do the prime factorization of both the numerator and denominator, we get 5 times 3 times 101 for the numerator and 2 raised to the power 2 into 5 raised to the power 2. Upon further reduction, 5 and 5 will get cancelled. We get minus 3 times 101 by 2 square into 5. Okay, so now we are able to see that the fractional form of this decimal number, terminating number, has the denominator which can be written in the form of 2 in terms of 2 and 5 only. That means the prime factors of this denominator comprises of 2 and 5 only. As stated in this condition, it should be 2 to the power n and 5 multiplied by 5 to the power m. So here n is 2 and m is 1. 5 raised to the 1 and 2 raised to the 2. Hence, this property proves. Now let us talk about the other type of non-terminating number and see which property applies to them. Now, if we're talking about non-terminating and repeating, what do you think should be the property of the fractional form of this kind of decimal? If it was this for the terminating part, for the non-terminating, it should be the opposite, right? And it is the opposite. It means that for the non-terminating number, for the non-terminating and repeating decimal number, the fractional form of that number must have a denominator which cannot be represented in this form. Understood? That means if a number which is non-terminating, which goes on forever and its digits repeat, if you convert it into the fractional form, you will see that the denominator of that fraction will not comprise of just 2 and 5. The prime factors of the denominator won't be 2 and 5. Such numbers will have a non-terminating and repeating decimal expansion. Let us take an example to make it more clear. Let us take 4 upon 70. 4 upon 70, the decimal expansion of this is 0. It is quite complex. 0.0, a very large set of digits repeat. 0, 5, 7, 1, 4, 2, 8. This set of digits repeat. So again you will get 5, 7, 1, 4, 2, 8. When you take the prime factorization of the numerator and the denominator, you get 2, 5, 7. Upon further reduction, you get 2 by 5 times 7. Now, as I told earlier, the fractional form, this is the rational or the fractional form of this decimal number, where this is P, this is Q. Now, as you see, Q does not contain just 5 and 2. It also has a 7. Hence, it does not follow this. It does follow this property. That means it does not have a denominator which comprises only of 2 and 5 as its prime factors. Since it does not have this property, it does not follow this property, it has a decimal expansion which is non-terminating, which goes on forever and is repeating. The digits repeat.